Second part of Unit 3, we're going to go on to shapes. Polygons and circles is a fancy way of saying we're going to do some shapes today. Okay, lead you in nice and gently. Last week we did the angles, now we're going to start adding the angles together and making up some shapes. Shapes all around us in the real world, you see them everywhere. It's a requirement for us to be able to describe things correctly. As far as your GCS exam is concerned, you're definitely going to get a shape that you're going to have to either identify or do some kind of moving around with. Okay, so that's what today's going to be all about, shapes. 3 objectives are recalling the properties of shapes. Really, that's what that first one's saying. We're going to look at all the shapes, and while we're talking about shapes, I'm going to delve into a little bit of 3D shapes, because in a few weeks' time we're going to be doing volume and capacity. So I'm going to touch on these 3D shapes to give you a heads up, because some people struggle with 3D shapes. So if I give you them today, let it rest for a couple of weeks and give them again, hopefully they'll settle a bit better on the names and what they're all about. That first objective kind of lasts a couple of hours. It's been lasting about 2 hours, that one. This one is about 10 minutes. This is talking about the labels of things for circles. So one of the shapes we're going to look at in detail today is a circle, and we're going to talk about some of the labels for circles, things that we call things on circles, 10 minutes max, and then this one's about 20-30 minutes, and that's talking about the circumference and areas of circles, so using a bit of maths with these shapes. Okay, so it's quite smart recap for today. List 4 types of triangle and their properties. That's your first question. You will need to write these down. And what is the sum of the interior angles of those 2 shapes? Let's cover these quickly then. So the 4 types of triangle. Give me a triangle in each triangle. Sorry?
Equilateral.
Equilateral. So an equilateral triangle is one of our triangles. And what makes something an equilateral?
You're up to 180.
Sorry?
All 3 sides add up to 180.
Any triangle, they all add up to 180. Okay, so that's
No,
a general
60.
rule, but what makes something very
So
specific?
60.
They're all 60, so all of the angles are the same, and what else is the same? All the sides are the same, and they go hand in hand. So if you end up with a triangle with all 60 degrees, you know it's equilateral, all the sides are the same. If you have a triangle with all the sides the same, you know all the angles are 60 degrees. Good, that's the first one. Give me another type of triangle.
Scaling.
Good, what's the scaling?
It's the one that...
It's gone off already, miles
it's
off.
the dodgy one, isn't it? The one with the sharp corner, and then you can have it on, like, you know what I mean? Like the angles.
So what makes a scaling triangle a scaling
one
triangle?
One could be 170, the other one could be 8, the other one could be 7.
Brilliant, so they're all
different.
brilliant. So they've all got different angles. If all of the angles are different, the sides must be different. Yeah? So remember that, because you get a lot of these questions where they'll give you a triangle with different angles and say, why is this length not the same as that length? Because if the angles are different, all the sides must be different. Okay? In your homework, I think there was something like that. So equilateral scaling, back over to this table.
Isosceles.
Isosceles. Spell it. Okay.
I-S-O-S.
I've got it, I'm joking.
It's a weird name.
Isosceles, and what's the property, what makes an isosceles triangle?
2 sides and 2 angles are the same.
Yeah, and they go hand in hand. So if you get a triangle where 2 angles are the same, 2 of the sides must be the same. Okay? Or conversely, if 2 sides of a triangle are the same, then 2 of the angles must be the same. Okay? They go hand in hand. Last triangle then.
Right angle triangle.
Good. So we've got the right angle triangle. Quite obvious. What makes a right angle triangle? A right angle. Good. So they're the 4 sorts of triangles, and we're going to sort of touch on those again today. Let's look at these shapes then. Interior angles of shapes. Drew, interior angles. What do the interior angles of that shape add up to?
360.
360. So last week we talked about a 3-sided shape, or a triangle, as Adam said earlier, always has 180 degrees. Okay. A 4-sided shape has 360 degrees, and that shape over there, what's the interior angles of that shape? What do they add up to?
Yeah, 90 on each.
540.
If it was 5-sided, we decided we were always adding 180, so if it was 5 sides, it would be 540, but how many sides has that got?
720.
Good. So it's 6 sides, so it's 720, and we came up with a rule last week that said the number of sides minus 2 times 180 will always tell us what the interior angles of a shape add up to. So this has got 6, 6 minus 2 is 4, 4 times 180 is 720. Yeah? So you can either do this, start off with a 3 and a 4 because you know it's 180 and 360 and keep adding 180, but that does the same thing. That's what that does. Okay? Good. Okay, let's talk about two-dimensional shapes. We're going to start with two-dimensional shapes, we'll move on to three-dimensional shapes. Polygon. Fancy word for a shape. What does polygon mean? Anybody know what the definition of polygon is? Where it comes from? Who came up with it?
Multiple.
Brilliant. Not had that from anybody this week. I've been saying pretty poly, poly unsaturates, poly this, that and the other, and nobody's actually cottoned on that poly means many or lots of. Good. And then agon.
And we're going to guess a side.
Yeah, or corner. Okay. So it's all Greek to me. Poly means much or many, and agon is a corner, an angle, a knee. Okay. So many corners, angles, knees. Polygons come into two separate categories. Okay. Anybody think about the categories of polygons? So you've got lots of sided shapes, and we're going to stick them into two categories. Quite a difficult one to put across, right? What if I said to you a square and an equilateral triangle? What have they got in common? What does a square have?
They're all equal angles.
Not all, yeah, all equal angles, and all the sides
Same.
therefore are equal. Yeah. So if we've got a square and an equilateral triangle, we can group them together, and we call those regular polygons. Okay. So if all the sides are the same length, we call them regular polygons, like a regular hexagon, a regular pentagon. It means all of the sides are the same length. So if you've got regular on one side, anyone like to hazard a guess what's on that side? Ah, nice one, Sam. Irregular. So the main grouping of shapes are regular shapes and irregular shapes. And it's quite important that you understand the difference between the two, because most people assume or have a misconception that pentagons are always this nice even shape. And we'll have a look at that now. Okay. So we've got this shape here, which is hidden by my little progress thing. And this is anyone remember what that shape is?
Irregular.
It's irregular, and do we know what the name of the shape is? Anyone remember what the name of that shape is? Trapezium, yeah? One pair of parallel lines. This shape, and where does that live?
It's a regular.
What's the definition of regular? What did we say? The
All the
definition
sides
of
are the same.
all the sides are the same. A rectangle, all the sides the same.
No.
So it goes over the other side. Irregular. Equilateral triangle.
Regular.
Scalene triangle.
Irregular.
Square.
Regular.
And this shape here. Regular, because it's a regular hexagon. Okay. Good. Good. What I'm going to do now is I'm going to show you something called Pecha Kucha. And it's a Japanese form of presentation. When you get these software designers who want to sell something to Sony or Samsung or whatever, they are given 6 minutes and 40 seconds in front of the chairman of the board to sell him something. And what they use is this form of presentation called Pecha Kucha. And what it is, it's PowerPoint. And every slide has to change after 20 seconds. And there are 20 slides, so it gives us 6 minutes and 40 seconds of presentation. Okay? And you've got to sell something to the chairman of the board. So I'm going to show you Pecha Kucha, just in case you want to use it, if you come across it in the future, if you're doing teacher training or whatever, or you've got to give a 5-minute presentation, you might think of this as a good way of doing it. So I'm going to show you how it works, and I'm going to sell you two-dimensional shapes. Okay, good morning everyone. Today for my Pecha Kucha presentation, I'm going to cover the subject of two-dimensional shapes. Shapes are all around us in our day-to-day lives, but how many of you can identify the correct names of the basic shapes that we see? The objectives for this presentation on shapes comes from the GCSE and Adult Numeracy core curriculum and are part of the Maths Measurements, Shapes and Space section. Specifically this morning we will cover a subsection at foundation level where we're required to recognise two-dimensional shapes. The D in 2D stands for dimensions, and in a 2D object the two dimensions are height and width, making the shape look flat. All of you will have heard of 3D, like 3D films. The third dimension is depth, which we will cover later on in this lesson. So why is it important to identify and describe the shapes? Shapes surround us in the natural world and in the designs of the man-made world. You need to be able to correctly identify these shapes as students when taking instructions and preparing designs for customers. Let's start with a really common two-dimensional shape, the square, and look at some of the terms used to describe a shape. A square is made up of 4 equal length sides. The fact they are equal makes it a square. There are 4 corners where each of the sides meet and 4 right angles. Let's look at another shape that you'll be familiar with in the real world, a rectangle. Again, the face of each brick has 4 corners, 4 angles and 4 sides, but this time 2 of the sides are longer than the other 2. Let's see if you can guess the next shape from the blunt description before the Muppet does.
I saw 3 angles, of that I'm sure, and I saw 3 pointy corners, and then I saw 3 straight sides. The top was very narrow and the base was oh so wide.
Wait, that sounds like
A triangle!
So, to put it bluntly, a triangle is made up of 3 angles, 3 pointy corners, and 3 straight sides. The top was very narrow, and the base was oh so wide. Again, we use the common terminology to describe our shapes, but this time there are various types of triangles we need to consider. The 3 main categories are equilateral, where all of the sides are equal length, and therefore all of the angles are 60 degrees. Isosceles, where 2 of the sides are the same and 2 of the angles are the same. And finally scalene, where all sides are different lengths. There is a special one. No, not him. I mean a special triangle. The right-angled triangle, which has one angle of 90 degrees. There's a clever trick to work out the length of all the sides and calculate the angles, which is extremely useful in construction. One of my Greek relatives, called Pythagoras, is credited with that little gem. Now the exception, the circle. No corners, no angles, and only one side. Maybe the more observant would say it has 2 sides, the inside and the outside. Some would say the circle has given us our greatest invention, the wheel. However, personally, I think the square wheel will one day will really take off. So what do these basic shapes we've seen so far do for us? Well, they make up codes in our lives. For example, with traffic signs, triangles are warnings, circles are instructions, and squares and rectangles provide us with information. Now for something a bit more challenging, polygons. The word polygon is, like most good things, derived from Greek and literally means many corners or angles. Squares, rectangles and triangles are all examples of polygons, but there are far more of them out there. Polygons can be broken down into 2 main groups. Regular polygons that have all sides the same length, like squares and equilateral triangles, and irregular polygons that have sides with different lengths, like rectangles, isosceles and scalene triangles. Let's have a quick look at the irregular polygons that you may have heard of. A parallelogram has 2 pairs of parallel sides, a trapezoid with only one set of parallel lines, and a kite that has 2 pairs of equal length sides that are adjacent. Now let's have a look at some of the regular polygons that you may have heard of. Again, a smattering of Greek will help. Pente, Greek for 5, gives us pentagon. A good way to remember this is the shape of the US military headquarters. Hex is Greek for 6 and gives us a hexagon, our 6-sided polygon. The Greek prefix process for naming regular polygons goes on and on and on. Heptagon is 7, octagon is 8, nonagon 9, and decagon 10, and so on. Now for the quiz, can you name the shape before the answer is revealed? How did you do in the quiz? Hopefully we've achieved the session objectives and now you can recognise the common two-dimensional shapes. Look around you and think shape. This concludes my presentation. Thank you. Are there any questions? That's two-dimensional shapes. Hopefully it's given you a taste of Pechacucha and an idea of some of the shapes that you're going to come across next. Okay? So let's have a look at some of these shapes then. So if we've got a three-sided shape and it's regular, that regular three-sided shape is it's an equilateral triangle. If it's irregular, it's isosceles, scalene, or so on. Four-sided shape, does anyone remember what we call a four-sided shape?
Quadrilateral.
Good, quadrilateral. We're going to come on to them later. If it's got all the same sides, it's a square. If it isn't, it can be anything. A trapezium, a trapezoid, a parallelogram, all these other things. And we'll look at all those names in a minute. Five-sided shape, pentagon, yeah, cheers John. Most people when you say the word pentagon think of this shape here because they're thinking regular pentagon. Be aware you can get irregular pentagons. Yeah, this thing here doesn't look anything like that thing there. And especially when you get bigger shapes. So this shape here, hexagon, so regular hexagon, irregular hexagon, just six-sided shape. Okay. And then finally, last one. I told you it's got 8.
Octagon.
Octagon. What is it? Hex. It's got 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. It's got 8. So we're talking octagon. So regular octagons. This is an octagon. It's just an irregular. So get this regular, irregular thing into your head, okay? Because when you're describing them in the exam, you'll probably have 2 marks for describing it. One for octagon and the other mark for regular or irregular. So try and be specific when you're giving names of shapes. Good. Just going to fire through the 2D shapes really, really quickly, see if we know them all, because there are 1 or 2 in here that we actually haven't talked about yet. So, go just start from the top left, Sam, and we'll just zoom around. Square, Drew,
Rectangle.
Adam, oval or ellipse. Everyone happy with that? Yeah. Where are we? Anthony on this one.
Triangle.
Which sort?
Equilateral.
Good. Sam.
Is that an isosceles?
Good. Isosceles. Drew.
Scaling.
Good. Next one.
Right angle.
Adam. Right angle triangle. You know what this one? This is a square on its side. Okay. So think of a square on its side. This is one of their favourite shapes in the exam. So you've got a square, and we've just tilted it over a bit.
Irregular square.
It's got a special name, and it's one of their favourite shapes in this exam because it's got a lot of properties that a square has, which you'll find out in a minute. Anybody help him out? Square, just tilted on its side a little bit. See if the whole thing's moving. Anyone heard of a rhombus?
That's it, rhombus.
Right, a rhombus. You will remember rhombus because it appears at least a couple of times in your homework, and I'm going to constantly go on about the rhombus because it comes from a square, it shares a lot of properties with a square. So a rhombus is a square on its side. Whereas the next shape along, Anthony?
It's a rectangle on its side. I don't remember what it is. Probably
It was in the presentation, the one that you were querying.
Parallelogram.
Parallelogram. So a rectangle on its side is a parallelogram. Yes, John?
Does not parallelogram not have the little arrows on the two?
It can do to show that they're parallel.
But
Yeah.
it doesn't always have to.
Not always, if it's obvious like that.
Right.
Okay, if they're not asking you questions about angles and stuff, if they just say it's a parallelogram, they are parallel. It's like a square. You don't put
Yeah.
the parallel symbols on a square.
Yeah.
They'll only do that if they're trying to help you work out an angle with what we were doing last week. So a parallelogram is a rectangle on its side. So square on its side is a rhombus. Rectangle on its side is a parallelogram. Next one along, Sam.
Is it trapezium?
Yeah, trapezium, trapezoid, trapezium, where it's got one set of parallel lines. So one set of parallel, the others we don't care about. Next one, Drew.
Kite.
Good. Kite. Next one,
Pentagon.
pentagon. Next,
Excellent.
hex.
Octagon.
Anthony, octagon, and last one, Sam. There's 10 if I tell you.
I haven't got a clue.
Decan.
Good. Decade, decagon for 10.
What's a tetragon?
Tetra, I don't know, tetra.
It's just one of them that's many. You can
Many.
make it.
It's 14,
Like,
I think.
groups of loads.
Is it? Lots of sides.
I
don't know.
thought it was
I'd go
14.
polygon myself, not tetragon. Right, I'm going to teach you something now. Stand me in good stead tomorrow, right? What shape is that? What have we just been talking about? If all the sides are equal? A rhombus. If I do this with a rhombus, try and shrink it down evenly. Okay, just turn it like that so it looks. What shape is that?
Kite.
It's not a kite because a kite's different adjacent sides.
Diamond.
Okay? It's a rhombus on its end. Yeah? So when you're doing question and it gives you something like that, think about it just being rotated through 90 degrees. Okay? Don't use the D word. I don't. Okay? It will stand you in good stead, trust me.
Really, there's no such thing as a diamond at all.
Not in the GCSE descriptions of the shapes that you've got. There is a diamond, of course there's a diamond, it's a physical object, but there's a descriptor at GCSE level. We don't use the word diamond, we use a rhombus, yeah? Because that's all they're saying it is. And a video I'm going to show you, the guy actually uses the word diamond, and he shouldn't do. And he also makes another mistake that I'll point out. But as far as your syllabus for this exam is concerned, when they do that, don't call it a diamond, it's a rhombus. Yeah, it's just tilted on its end. Okie doke. So that's that one done today. So we won't mention the D word again. What we're going to do now is test how good you are at recognising these shapes from descriptions, which they could well do in the exam. They could give you a series of descriptions on one side of the page and ask you to join them to the matching shape on the other side. So 4 sides all with the same length. You could say a square, 3 sides all with different lengths, a scaling triangle and so on. So I've got a set of sorting cards. You can do them on your own, I've got enough, or you can do them as a pair. Last week we covered interior angles. We also need to cover something called exterior angles, and there are some rules that we can use, okay? We'll just have a recap on last week. We worked out that we can work out the interior angles on any shape based on the number of sides. So if we have a 5-sided shape, we use this equation, n minus 2 times 180, to work out that on a, what shape is it? Pentagon, the interior angles are all add up to
480?
So it'll be 360 plus 100.
40.
good. So the interior, the total of the interior angles is 540 degrees. Okay? If this is a regular pentagon, what is each one of those angles then? What do I have to do to my 540 degrees?
Divide by 5.
Divide by 5. So what's each angle worth? And this is going to be important throughout this lesson on a pentagon.
108.
Yeah, can use calculators, please. If you haven't got one, ask, I'll get you one. So each angle in here is worth 108 degrees. So the interior angle on the pentagon is 108. The total of the interior angles is 540. There's another trick you can use. If you don't want to work out the interior angles, you can actually use something called the exterior angle. The exterior angle is the angle produced when you extend the line of the side and measure the outside to where the next line starts.
72.
And how did you get 72?
Because the line has 180 and there's 2.
So you knew this one from what we've just done is 108 and that's 72. Perfect. Using last week's rule, absolutely perfect. There's another rule you can use if you want to work out an exterior angle. And that is the fact that whatever your shape, your exterior angles always add up to 360 degrees. So if you've got a pentagon, I've got 360 degrees and I divide it by 5 sides, number of sides. So what does that tell me my exterior angle is? 360 divided by 5.
I don't know.
72.
Funnily enough, it's 72. So that kind of proves that particular rule. So you can actually use another rule. So you've got an interior rule There's also an exterior rule. Okay, so if you want to find the exterior angle of a particular polygon, the exterior angles will always add up to 360
Doesn't matter
degrees.
what shape it is, it always-
No, so if we have, let's pick another shape then, a really bad hexagon. Got a hexagon. Okay, what are the interior angles of a hexagon? What do they add up to using our interior rule?
6.
720 degrees, because it's 6 minus 2, which is 4. 4 times 180. So the interior angle of a hexagon is 720. So if it was perfectly drawn, what would one of those angles be?
6.
120.
Brilliant, because we divide it by 6 and it gives me 120. So each one of those is 120. So if we look at our exterior angle,
60.
and we look at that, using your 180 rule, it says 60, yeah, because it's on a straight line. If we use this rule here, 360 degrees, divided by 6, it gives us,
60.
there you go. Magic. Isn't it magic? All these rules to do the same thing. Yeah. Okay, so exterior angles. So don't just think interior, think exterior as well. Right, you'll love this exercise. Not a lot. What I'd like you to do is I'd like you to get your chairs and sit back to back. And what's going to happen is I'm going to give you a card with a shape, a random set of shapes, right? And one of you is going to be the describer and the other is going to be the drawer. I'm going to concentrate now on these four-sided shapes, these quadrilaterals. We've already talked about them being four-sided shapes, so I'll not insult your intelligence. Okay? It's a fancy term for a four-sided polygon. And there are quite a few of them. Now, we need to know the basics on them, but the trickiest part of what you're going to do today is also going to involve quadrilaterals. Okay? So let's do the basics. Let's name them again, just to reinforce the names that we've got so far. So, quadrilaterals, top left. Anthony, I'll let you start with the easy one.
Square.
Square, next one along. Sam?
Trapezium.
Trapezium, good, because it's got the two parallels. Next one, Adam?
Rectangle.
Rectangle, good. Next one, Drew?
That rhombus. Is it
Yeah, it was, sorry, you said it first time?
rhombus?
Rhombus, yeah, good. A square on its side. This one, Sam?
Height.
And John, last one?
Parallelogram.
Parallelogram. Excellent.
I'll always
So they're the
forget.
basic names. You will need to know them.
I'll forget. I always do that.
Parallelogram.
Parallelogram.
Two sets of parallel lines. It's a rectangle on its side. So you know you think a rhombus, square on its side.
Yeah.
Parallelogram. We'll do some bricks and we'll just put 2, 1. I love these things. Nicked them off my nephew. Really good for this. Yeah. So put 2, 1, 2, 1 to join them. A couple of balls. And just, it's easier to visualise shapes, okay? So if I leave you with that, so that's a rectangle on its side. Parallelogram, rhombus, square on its side. So if you struggle visualising these things, that's all we're doing, okay? And those will come in useful in a minute because we're going to look at the properties of quadrilaterals. Okay? I'm going to show you a video now of the basics that we covered last week on quadrilaterals. So we're going to look at lines of symmetry and orders of rotation just as a memory jog on what we did last week. And then we're going to do the hard bit and we're going to talk about something called diagonals. I think Sam will remember this from last year. Okay? So, just going to show you a video just to remind you, and there are two errors in here. The first one is the D word, and the second one is he gets something wrong towards the end, and we'll highlight that at the end of the video, okay?
You give me that, my USB as well.
Yeah, it's alright, don't worry.
Okay, triangles, 3 sides. Quadrilaterals, 4 sides. There are 6 types of them that you need to know. I am a little bit excited. Right, here we go. Square, rectangle, rhombus, parallelogram, trapezium, and kite. Let's start with the square. All 4 sides of the square have equal length. They also have 4 equal angles, all of which are 90 degrees. There they are. They have 4 lines of symmetry, one here, one here, one here, and one here. They also have rotational symmetry order of, well, there's 1 and 2, 3, and 4. So rotational symmetry order of 4. Rectangles are a bit like squares that have been stretched. Here's one. they have two pairs of equal sides. So this side and this side, and this side and this side are equal. All four angles are right angles. There they are again. They have two lines of symmetry, one here and one here. They also, if we rotate it, you'll see have two positions where they look the same as you rotate them. So they have rotational symmetry order of 2. Here is a rhombus. It's just a square that's been pushed over. These arrows here mean that the sides are parallel. This just means that they face the same way. So this side and this side are parallel, and as you see with these arrows, this side and this side are parallel. So it has two pairs of parallel sides. If I spin it around like this, you'll see why it's also called a diamond. It has two lines of symmetry, one here and one here. And just rotate it around. One position where it looks the same. Two positions where it looks the same as you rotate it all the way. So it has rotational symmetry order 2. Time to look at a parallelogram. Here's a parallelogram, and it's a fun word for a rectangle that's been pushed over. Like a rhombus, it has two pairs, one there and one there, of parallel sides. Only unlike a rhombus, it has no lines of symmetry at all. Just rotate it around here. There you go, one position where it looks the same. Two positions where it looks the same as you flip it around, so it has rotational symmetry order of 2. What about trapeziums? There's one, and there's another one, and there's a third one. All trapeziums have one pair of parallel sides. There they are. Most trapeziums don't have any line symmetry, but one type of trapezium does. It's an isosceles trapezium, and it means that these two angles are the same, and there's the line of symmetry. So most trapeziums have no lines of symmetry, except isosceles trapeziums, which have one. However, no trapeziums have any rotational symmetry. Finally, there are kites. Here's one, and they have no parallel sides, but this angle and this angle are the same, and they have a line of symmetry down here. When you draw it, you can see that a kite really just looks like two identical triangles, this one and this one, that have been stuck together either side of the line of symmetry. Kites don't have any rotational symmetry though. Another super handy table for you, showing all the properties of these different types of quadrilaterals. As you go down, the pairs of parallel sides get smaller, lines of symmetry get smaller, and the orders of rotational symmetry get smaller. Other than that, it's pretty self-explanatory, except this little note here where it says trapeziums have no lines of symmetry. That's almost true, except for isosceles trapeziums, which of course have one line of symmetry.
Other than the D word, what was the other mistake or error that he talked about?
Things got smaller.
Sort of. It was. Anyone else spot
Wasn't the
it?
parallelogram bit, was it?
It was at the end, towards the end, trapezium and kite. When he was doing the verbal commentary, he said, how many orders of rotational symmetry? He said they had no rotational symmetry. In the commentary, twice, for the trapezium and the kite, he said they have no rotational symmetry. They do, everything does. Everything has at least a rotational symmetry of 1, and in the table, it shows 1. So the table's correct, but what he said in the video wasn't correct. He said they had no rotational symmetry when they do. Everything does. Everything was back on itself.
That CGP can be a bit too dumbed down.
Yeah.
And a bit too.
But it's saying that
inconsistent
16 to
sometimes,
18 is
yeah.
taking their GCSEs. It's not an adult thing in so much as the way they
I've
talk at
noticed
you
other bits
sometimes.
and pieces in there though that
Yeah.
sometimes like they've skipped something or it's not always great.
No, but it's a nice plug-in for a lesson just to use the odd
Yeah.
bit. I wouldn't use it solely for revision. So for Adam, I know you like it. Just don't get too carried away with it. Oh. Okay, let's carry on and then take a break. Let's just do a little bit more and then take a break. So, quadrilaterals, as he said in the video, you can draw a line from one corner to the other and it creates two triangles. That's something we already know. Any four-sided shape has an interior set of angles worth 360 degrees. This is another way of showing it, because when you cut it in half, it makes two triangles. One triangle is 180, the other triangle is 180. It's the same way of talking about the same thing. Let me get rid of that noise. Okay. sorts of questions they could ask. It goes back to what we were doing last week, really, where they can ask you for the various missing angles on shapes. So here, I've got angles A and B that I want. Let's start with the easy one. Which is the easier of those two to get?
B.
The B, because we've got a rule to get that really quickly, which is 180 minus the 78 gives us 102 degrees. Perfect. For angle A then, we have a rule that tells us how to work out A.
Add up
The angles, so 110 plus 88 plus 78 is
98, so that'll be 176.
276. And what do we do with our 276?
Might take it away from 360.
Take it from 360 and it gives us 84 degrees. So the missing angle there is 84.
No, you
Okay,
can't.
can use your calculator. Please start using your calculator for Unit 1. Homework marking yesterday afternoon. People are still adding two simple numbers together wrong. Okay, got a calculator, use it. Again, there are some various rules thrown up and some rules we used last week that can really help us for angles on quadrilaterals. So if we look at shape, the first shape in the top left, if the bottom left-hand corner of what shape is that? Are they the same length, that and that? Parallelogram, okay? It's showing you that that's parallel to that, that's parallel to that, but they're different lengths, aren't they? So it's a parallelogram. So if this angle is 42, what do we think the angle in the top right-hand corner is going to be? 42. Because the angles happen the same, because you're flattening it. If you look at our little magnetic shapes here, when you've got your rectangle and you can see the nice 90 degrees, as you start flattening it, this angle and this angle are doing the same thing, while this angle and this angle opposite are doing the same thing. So with a rhombus and a parallelogram, when you start flattening it, the opposite angles are still the same. Yeah? This one's getting smaller, this one's getting bigger. Okay? Next shape. If this is 65, what's B? 65, be careful what? They add up to 180. This is the interior angle rule from last week. The two interior angles on a parallel line, so this is parallel with that, add up to 180. So it's 180 minus 65, which is 115. Does that make sense? Can you see where we've got that angle from? So that comes from a rule we learned last week where the interior angles, okay? Another way of doing it, if this is 65, what's that angle up there? 65, we've just discussed that bit. But you could add them together and work out from 360, take off the 265s, and then whatever's left divide by 2, and it gives you 115. Good. Here then, they want these two angles. Which is the easy one to do first? D, and that's the, which rule?
The 180 rule.
Good, so 180 minus 114 leaves me with, clickety-click, 66. And if that's 66, we can work out E from
188.
114 because it's our interior angle rule again. Good.
You could do the Z one as well.
And brilliant, the Z. So we've got the alternate angle. The Z angle, as some people called it last week. Yeah, because this is parallel and that's parallel, it creates this angle is the same as that angle. Alternate angles. Okay. Finally, F, angle F. How would I calculate angle F? Properties of a kite. Which angles are the same on a kite, which are different?
They're both 90 degrees, aren't they?
Brilliant. So that's your starting point. You need to know on a kite that those two angles are the same. So they're both 90, so that gives us 180. So we just started there. If I know that's 90, I know this is 90. I've got two 90s, which is 180, and I know the top angle is 138. So I know those three angles add up to 318. It's a quadrilateral, so all the angles add up to 360. So 360 minus 318 gives us 62 degrees. Okay. So quadrilaterals have their own properties that allow you to solve these angle problems that you might get. Okay, last bit before the break, and then we're done. We need to consider something called the diagonal properties of quadrilaterals. So I've got my square here, and a diagonal is a line that goes from one corner to the other, and you do that for both of the sets of corners. So you create these crosses on your quadrilateral. Okay. When you do that, it does a couple of things. A couple of things they're going to ask you about. The first one is called bisecting. Does anyone know what bisecting something is? Cutting it exactly in half. So if we look, okay, at bisecting and we look at our diagonal, so let's look at our diagonal. Okay, diagonal, no, I'm VOing. I did this yesterday. Let's look at the diagonal. Is the diagonal cut in half by the other diagonal? Does it chop it exactly in half? It does, yeah. Okay? So you have to look at bisecting the diagonal. The other thing you have to look at is bisecting the angle. So I've got my 90 degrees here. When I draw my diagonal, does that diagonal cut that 90 degrees exactly in half?
That one does.
On a square, it does. Okay? It cuts it exactly in half. So when you talk about bisecting, you bisect a diagonal and you bisect the angles of the quadrilateral. The last bit, where the two diagonals cross, are they perpendicular? What's perpendicular? Remember from last week?
So it's 90 degrees.
At 90 degrees to it. So another question they could ask you is, do the diagonals cut perpendicular? In a square, do they cut at perpendicular? Yeah, because where they cut, we get a nice right angle there. Okay. So those questions can be asked about any quadrilateral, and that's what we're going to do next as a little exercise before the break. Okay. You're going to get asked 4 questions about a quadrilateral that I'm going to give you. And I'm going to do the easy one. I'm going to do the square, and I'm going to talk you through what you need to answer on the questions, okay? So we've got 4 questions to answer. What you need to do when you get your piece of paper with your quadrilateral on is draw your diagonals, okay? And I'm doing the square. I've chosen the easy one. And you need to answer these 4. Let's go through the questions, and this time we'll populate a table, okay? We'll do this ourselves, and then I'll give you the handout that's got the answers on. So, are the diagonals equal on a square? Yes. Do the diagonals bisect each other? Yes. Do the diagonals cross at right angles? Yes. And do the diagonals bisect the angles? Yes. So let's go around. Who's got the kite? So diagonals go from corner to corner, not from midpoint to midpoint. It's all right. John, you've got that one as well.
No.
Help Anthony out. So, are the diagonals equal? No. Do the diagonals bisect each other?
No.
One of them does, the other doesn't. If you look at a kite, if we look at our kite and our diagonals on a kite, this one is cut in half, but this one isn't, if you catch my drift. The one that goes from left to right is cut in half, isn't it?
Right.
But the one that goes up and down isn't. So it's sometimes, isn't it, on that one?
Right, okay.
So one is, the horizontal one is, the vertical one isn't. Do the diagonals cross at right angles?
I wasn't sure because it depends on the top angles, doesn't it?
It shouldn't, it's straight up and down, straight lefty righty.
Draw it out each, yes.
It will always, a kite should always, because that length is the same as that, that's the same as that.
Yes,
Then that coming straight down, that going straight across should create right angles every time. So that should be a yes. Do the diagonals bisect the angles of the quadrilateral? So, is this angle here cut in exactly in half by the line going up and down?
Yes.
Yeah, and the one at the top is, but what about these ones at the sides?
No.
No, because it's slightly less steep on the ones above. So that's a sometimes as well. Okay, parallelogram. Who's our parallelogram person? Sam. So let's try and get these done. Are the diagonals equal? No, because as you close this down here, the distance from here to here is getting bigger, and the distance from there to there is getting closer, isn't it? So that's correct. No. Do the diagonals bisect each other?
Yes.
They do? Happy with that?
I said yeah because they cross in the middle.
They're crossing. Yeah, the question is, if you've got an angle here, is that angle cut exactly in half? And it shouldn't be because it's just a rectangle that's getting longer. Yeah. So it should be a no. And then do the diagonals cross at right angles?
Yeah.
Yeah. And then do the diagonals bisect the angles of the quadrilateral?
No.
Okay. And then trapezium. Who's got the trapezium? Drew, you got the isosceles trapezium or the trapezium trapezium. You got the trapezium, you got the isosceles trapezium.
Yeah, right, yeah.
Go on in time really quickly. Are the diagonals equal? No. Are the diagonals do they bisect each other? Do the diagonals cross at right angles? And do the diagonals bisect the angles of the quadrilateral? Drew, isosceles trapezium. Are the diagonals equal?
No.
No. Do the diagonals bisect each other?
Yes.
Do the diagonals cross at right angles?
No.
And do the diagonals bisect the angle of the quadrilateral?
No.
Okay. Rectangle. Anyone got a rectangle?
I've got
Adam?
that tangle.
So, rectangle. Are the diagonals equal?
Yes.
Do the diagonals bisect each other?
Yes.
Do the diagonals cross at right angles?
No.
And do the diagonals bisect the angles?
No.
Finally, anyone got a rhombus? Nobody's got the rhombus. I'll do the rhombus. Are the diagonals equal? No. Do they dissect each other? Yes. Do they cross at right angles? Yes. Do the diagonals bisect the angles? Yes. The reason they like the rhombus so much is because it's got a lot of qualities like a square does. Okay? Because it's a square pushed on its side. You will get a lot of questions on a rhombus. Right. I think I'll give you the handout and we'll take a break. We're about an hour and a quarter in, aren't we? Brilliant. Okay. Just going to touch on something called tessellation. Anybody heard of tessellation before? Yeah? Tessellation, posh maths word for tiling. There's a couple of golden rules for tiling. The main golden rule for tiling is when you have shapes that tessellate, they have to do something. What's that something? What can't you have when you tessellate? A gap. So what do they all have to add up to not to have a gap?
They all have to be together the same size. Same
Yeah.
shape.
So where they meet, what do they have to add up to? 360 degrees. So this shape tessellates. We'll talk about that in a second. These shapes tessellate because if you think about it, I've got a square, so that's 90 and 90. See what I'm saying here? 90 and 90. That's 180. That's where I'm on a straight line. And these three equilateral triangles, 60, 60, 60, that's the other 180. So the reason things tessellate, or tile, is because the angles add up to 360 degrees. They will try and trick you in the exam because there's a shape, okay, that they will always give you and say, does it tessellate? And 9 out of 10 of you will say yes. Does the pentagon tessellate? Why doesn't the pentagon tessellate?
It doesn't add up. No, it doesn't add up to 300.
What's the interior angle of a pentagon that we've done about 10 times today?
72.
So you've got 108 degrees there, haven't you? So if I had another pentagon, really quickly, rotate it. What are the two angles that meet add up to now?
Not
216. And if I had another pentagon, what are they going to add up to? 324. So I have 108, and I have another 108, and I have another 108. I'm up to 324 degrees. So it leaves a gap of 36 degrees. So pentagons do not tessellate. Got that? They will trick you.
So if you just put no, I know it sounds daft, but if you just put no, they don't tessellate.
If they give you 2 marks and say, does this shape tessellate, explain why? Then you say, no, that's 1 mark, because the interior angle is 108 degrees, 308 is 324, it leaves a gap of 36, or something along those lines, okay? So let's look at another shape then. This shape,
That's fine. Yeah.
what shape is it?
Hexagon.
Hexagon, what's the interior angle of a hexagon that we've done?
220.
120. So what are 320s?
3 hexagons.
320.
360.
360. So a hexagon, if I can grab it off, tessellates very nicely, thank you.
Why though? I know it sounds daft, but why is the pentagon not? Because it's 5 sides, or
No, it's the interior angles. This is
That's
exactly
all
what
it
we were
is.
saying about the angles. The interior angle is 108. Does 108 go exactly into 360?
No.
It goes 3 times the remainder, 36. So there's a 36 degree gap. The interior angle of a hexagon, as you just told me, is 120. What are 320s?
360.
360, which is why it does tessellate. Does that make sense? Yeah?
So
So,
basically, you just can't fit another shape in, can you? On that one, on the left-hand one.
on the left one,
Yeah.
well, you can't get another you can put
Yeah.
a triangle or something in there if you had another
Yeah, but
odd
you can't put
shape,
an
but you can't
yeah.
put another pentagon in
Yeah.
there, can you? And that's what we're talking about. Does an individual shape tessellate? Okay, so be careful of that. Let's have a look at some other shapes then. But I don't need to do that. Really quickly, let's talk about tessellation. Square tessellates.
Yeah.
Circle?
No.
Nah. Triangle?
Yeah.
Yeah. Doesn't matter what triangle is. Because the interior angles on a triangle always add up to 180, you can always put one corner with another to make up. Okay? 360 or 180 initially. Rectangle does, that's dead obvious. Shape?
You could.
Yeah.
Yeah, trapezium does. If you think of a trapezium as the red shapes in here, so I've got a trapezium and a trapezium. Okay, they're the same shape. If you flip one over, tessellate. Yeah, it doesn't matter what the angles are, the other angles will match up. So you're going to end up tessellating trapezium. One that way, one that way. Does that make sense? Yeah? So trapezium does, rhombus?
Yeah.
Yeah, because it's the same. Or even a parallelogram does. Because I don't know if I've got any in here. There we go. Because it's got an angle like that, you just put the same angle next to it. There. Tessellation. Easy peasy, isn't it?
Yeah.
Just talked about this one, hexagon. And
Yeah.
what shape is it?
A rhombus.
Yeah, if it's different lengths, it's a kite. If it's the same length, it's a rhombus.
You only said diamond.
Ah.
I was just about to say.
Just to wind me up. Okay, brilliant. That's 2D shapes parked. What we're going to do today, we're going to talk about very briefly 3D shapes and recognising 3D shapes. In a few weeks' time, we're going to talk about 3D shapes again, but talk about volume. But today, I want to get a handle on their names. When we describe a 3D shape, we use certain terminology.
Like cubes and stuff.
Well, to describe how many things it's got. So this thing that's facing us, we call that the face. And this thing that goes from there to there, an edge, and where the edges meet, we call it a vertex. Excellent. So when we're describing three-dimensional shapes, we talk about faces, edges, and vertices, which is, if you flip your piece of paper over, what that's all about. So what we're going to do now is look at the 3D shapes that you need to know about. Okay? And you're going to fill in the properties on that sheet. So the first shape we're going to talk about is that one, the blue one. What is the name of that shape?
Cube.
A cube, and it's a cube because it's a square. Okay? And it has the same lengths on all of the edges and shapes and faces and so on. So it's a basic shape of a square with something behind it. Okay? And that's how I want you to think about 3D shapes, because when we come on to do areas and volumes of shapes, you've got to think of a three-dimensional shape as a two-dimensional shape with something behind it. Okay. So what's the basic two-dimensional shape that you're looking at? A rectangle. So the face that's facing you is a rectangle. Okay. So the face that's facing you is a rectangle, and it's got something behind it. That's all a 3D shape is. And what do we call this one? Cuboid. Very specific. A cube is all the sides are the same. Cuboid, a rectangle with something behind it. Have a play with the shapes if you want to. Pass them around if you want to. The next one. What's the basic shape on this? Cylinder. So a cylinder is a circle that has something behind it. That's all they are. Just so when you're thinking 3D shapes, think, what's my basic 2D shape? And it's got something behind it. The last one then, in the bottom right-hand corner. Slightly trickier. Some people get this one wrong.
Triangular prism.
Ooh, yeah.
Isosceles prism.
A triangular prism. Okay? The basic shape is a triangle. It's got something behind it. In theory, that's a circular prism, the cylinder, but we call it a cylinder. So a triangular prism is basically a triangle that's facing you with something behind it. So if you get this idea of the two-dimensional shape with stuff behind it, okay, you'll be doing volumes in a couple of weeks' time a lot easier, because we'll work out the areas of these basic shapes and just multiply it by whatever's behind it. And that's how we're going to treat 3D shapes. Let's have a look at some more 3D shapes then. What have we got here? What's the top left called then? This one here.
Square base.
Good. It's got a square as its base, so it is a square-based pyramid. So everyone recognises pyramid. So here we've got a square as your basic shape. Rather than having stuff behind it, the stuff comes to a point at the back. Okay? Next one then. What have we got in the top right-hand corner? Yeah, so it's a triangle that meets at a point. So it's a triangular-based pyramid. Okay, lots of good stuff going on. Next one, bit of a doddle. It's a sphere. Circle. Yeah, all the way round, sphere. Don't drop that on the floor, it'll probably crack. Okay, and then finally,
Cone.
circular based pyramid? No? What do we reckon? Cone. Cone. Okay, we call it a cone. Quite easily you could call it a circular based pyramid if you wanted to, because that's what it is. It's a circular base to a pyramid, but we call it a cone. Okay? So on your worksheet that I gave you a second ago, fill out the properties of the three-dimensional objects. If you need to see the object, just come and grab them. If you're struggling to visualise any of the corners, shapes and so on. So if you get stuck with a shape on the number of sides, edges and so on, just ask for them and we'll sort them out. 3D shapes, that's touching on them, getting their properties and their names. In a few weeks' time we'll be working out the volumes of most of those, okay? Not a problem at all.
Can't
Good.
wait.
And we've done that.
Oh, thank God. I've been waiting for that piece of thing there on that PowerPoint for ages.
Okay, just an hour, so we're about 10 minutes behind yesterday afternoons, or yesterday mornings. We're going to finish the lesson off talking about circles. The first bit is going to take about 5-10 minutes, and you need to be able to label the parts of a circle. Most of you should know the basic parts of a circle, okay, because these are the bits that we manipulate a lot in maths. So can anybody tell me the red line, the green line, or the blue?
Circumference of a circle.
Which one's what colour?
The circumference is the red
Good.
line.
So the outside of the circle we call the circumference. Pick a colour, green or blue. Green, what's the green one, Sam?
The radius. No, blue's radius.
Blue's the radius. So the radius is defined as a line from the centre point to the circumference. And then the green, diameter. And how do we define a diameter?
From one edge to going across the centre.
Good. So it goes from one side to the other, but it has to go through the middle.
Is that the circumference times diameter? No, circumference.
Don't start guessing. I'll tell you what it is in a minute when we do calculations. We're just doing names at the moment.
Oh, yeah.
So circumference, diameter and radius. So what's the relationship between the diameter and the radius? It's half. The radius is half the diameter. They will try and trick you when we start doing calculations in a minute by giving one when you need the other. Because we talk about the area and the circumference in terms of radius and diameter, and when you need one they'll give you the other to try and trick you. Okay? Have a look at this one. Think about the words that describe what we're pointing at. Some of them are common, some of them you won't remember, some of you probably never heard about. Anybody know any of the words that are on there that we're looking at? Less common because we don't use them very often in calculations.
An arc.
An arc. What's an arc? Which one's the arc?
The blue at the top.
Blue at the top?
Or the red. Oh wait, there's a red line. Is it the red line?
The red line, that one.
Or you were going to point to the other one, so go on the other red line.
The other red line.
Yeah.
So this bit here is called the arc, because I gave it away. Okay? The arc is part of the circumference. Yeah? Circumference goes all the way around, an arc is a little bit of that. Any others? Sam?
Is the segment the blue bit next to the arc?
The segment,
Or is that sector? No, it begins with
right,
S.
the two blue shaded areas are either the sector or the segment. And people get confused
Yeah,
between the
it's
two.
I'd say it's segment at the bottom.
Segment's the bottom. Who thinks segment is the bottom blue shaded area?
I think
Segment's
it's
the top
sector.
one, I think.
And who thinks the blue segment is the top? Segment is the top, and the sector is the bottom one. So a sector is like a piece of pie. In other words, it's the area from the centre out to the arc. And a segment is this area cut off by this line. And what do we call that line?
This is school, I can't remember it. My lord.
Chord.
Chord. Nice one, Sam, you remembered. It's the chord. Okay? And then the last one we have is this line that just touches the circle.
Is that the
Close? Begins with T.
That's transgender.
I know what it is, but I can't get it out.
Anyone heard of somebody going off on one?
Tangent. That's the.
Tangent.
People go off on a tangent. You heard that expression?
I thought it was like a beauty pageant. I'm thinking of a different word.
A tangent.
I was going to say transgent.
Right, a tangent is a line that just touches the edge of the circle. A straight line that touches the edge. You will need to learn these because every other exam they will give you a circle exactly like this with a load of lines pointing at them saying, label it. If you don't believe me, first question on your homework has, from a past exam, an exact same circle with a load of labels saying label it. And the only way to get them in your head is to learn them. Okay? So
Actually, if you sometimes I think that you get to like the middle point or something, and you think, oh yeah, they're not actually, and then they'll throw it in.
it's not going to be the first question, it could be halfway through. They did it on last year's. There you go. Okay? Every other paper, they know you know what a radius, a diameter and a circumference are because you use them in calculations a lot. What they want to know is, do you know what a segment, a sector, a tangent, a chord and an arc are?
Sometimes on last year's they give you, I think, a couple of names and they ask you to do the description or something like that.
Right, tell you
and
what they mean.
And then the other ones they'll give you like the description and then you'll have to put the names.
Put the names next to them.
Yeah.
So you know, like we did the matching of the cards earlier with the description with the name of the shape, they can give you a description with the name of a part of a circle. So that's another way of putting the exam question across. The one you've got in your homework is a simple label it one like this, but what they can give you is matching up. They'll give you a description and they'll give you the words and you've got to draw the lines and join them together. Yeah? Okay? So be aware you need to know those words. Right, Adam, you're nearly there?
I'm just trying to draw the picture at the same time, you know. I won't be a second, sorry.
Don't worry, you're going to get a handout in a second where you can write things down and stuff. You're going to write things down, aren't you?
Alright.
Okay? So this is typical of what they can give you. So D is what?
Segment.
Brilliant. A segment, not a sector. That's where people get confused. A.
Tangent. No, circumference.
Circumference. B.
Radius.
Radius. C. Is the chord. Okay? Good. And that is that objective done. 10 minutes max. Yeah? Really simple. You've got to know how to label a circle. I'm going to finish off, because we're talking about circles, with some basic calculations, and it will save us time in future lessons. Okay? So I'm basically striking while the iron's still hot. When you think of a circle, you need to think of this thing, pi. What is pi?
3.164?
3.14. In GCSE maths, when you do calculations and you see pi, the number you use is this, 3.14. It goes on forever. Does everyone know that pi goes on forever? 3.14159267887 blah 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 blah. It never ends. In your exams, when you're showing them you're working out and doing calculations and tapping into your calculators, use 3.14. What is 3.14? Where does it come from? How's it defined? What's 3.14?
I thought it was just a circle.
It's a circle.
It's from the.
That's why it's called pi.
It's from the outside of the circumference. You're going to discover pi right now. Pi is a ratio of the circumference to the diameter. In other words, this little exercise should have ingrained in your brains when you think about circles and pi, the fact that pi comes from the circumference of the circle divided by its diameter. And that is always this number, this ratio, 3.14. So whenever I ask in a class, especially GCSE class, what's pi, nobody ever says it's the circumference divided by the diameter. Everyone says it's 3.14. And a lot of people don't realise what 3.14 is. It's a ratio. It's the distance around the outside divided by the distance across the centre. Okay? And that's all pi is. Pi goes on forever. 3.1415926535897. It's never ending.
You couldn't even get to the end number if you tried?
No, can't.
So does it repeat or does it?
No, never repeats.
What? Do you mean the numbers never repeat? 1, 2. There's never a 1.
There's never a sequence of 2, 3, 4, 2, 3, 4, 2, 3, 4. It never repeats. Okay? And they've spent billions of pounds and many years trying to predict. They've got a software now that can predict the 20,000th number by putting some code in, but they don't know what's past that. It's mind-boggling. So we've just discovered that pi 3.14 is the circumference divided by the diameter. That's that little exercise. Hopefully the piece of string that's like tie the little knot in the piece of string and put it in your brains, okay? Yeah? So that's 3.14. So if I wanted to work out the circumference of a circle, so these questions can come at you in any way, and everybody remembers the fact that, oh, the circumference is equal to whatever. This is how you do it, okay? The circumference. How do I get the circumference on its own? Thinking back to algebra. Okay? What does C over D mean?
Circumference over diameter.
Yeah, over it. What's it mean mathematically?
Divide.
Divided. So it means C is being divided by D. I want C on its own.
Take the D away.
You don't take it away, you do the opposite. So what's it doing at the moment?
Times it.
Yeah, so at the moment it's dividing. So I multiply this side by D. If I do that, to keep it balanced, what do I have to do on the other side?
Same.
Times it by D. Okay? So to get circumference on its own, and this is what a lot of people remember, it's pi times the diameter, because we've done a bit of algebra with our pi. Okay? So you need to remember this. The circumference of a circle is equal to pi times the diameter. So let's do a really simple question to show you how this works. It's algebra. I'm trying to find out the circumference of this circle, so I don't know what C is. But I do know two other bits of information to put into my formula. I know what pi is. What's pi? 3.14. And I know what D is. So what does pi D mean? It means pi times D
So
times 10. Good. So you're cottoning on to this algebra lark, aren't you? Yeah? So the circumference is 3.14 times 10, which is 31.4. We don't need a calculator because we know how to multiply things by 10 really easily now, don't we? And what's the units? Don't forget the units when you're giving answers. Sometimes they'll give you the units written there. If they don't forget the units, okay? So that's the circumference of a circle. It's really straightforward. So here a little question for you, okay? A circular cake tin has a diameter of 22.5 centimetres. The lid is sealed with tape. The ends of the tape overlap by 1.5 centimetres. How much tape do I need to seal the tin? So how do we work out the circumference of any circle? What's the equation we use or formula?
Circumference divided by diameter.
Yeah, but this one here, if we're talking in terms of C,
pi
equals
times D.
pi times D. So this is the thing that's going to help us solve this one. So we're trying to work out the circumference. So what do we know? We know what pi is,
Which is 3.14,
and we know what the diameter of our tin is.
which is times 22.5.
So that gives me an amount of tape for the circumference to touch itself as it goes round is
70.65.
70.65, but I have to do something else because I don't want just the tape to go round and touch itself. I need to overlap, so I've got to
Plus 1.5.
add another 1.5 centimetres to give me.
72.15.
Okay. So the trick is work out the circumference, but then add on your 1.5 centimetres for your overlap. Okay. So can you see where you've got to start? It's a circumference question which you need to be able to recognise. They're not going to come out and just say, measure the circumference and add that. You need to realise I'm dealing with a circular tin. Think circle, think pi. To work out circumference, C equals pi D, and then fill in what you know and work out what you don't know. I'll give you another bit of
I
practice.
think it's because I didn't recognise that it was circumference. I think
Okay.
that's why I got a bit.
There'll be another question in a minute that will put a bit more straight to you. But what we're going to do now is I'm going to give you the area while we're working on these things. So if we're dealing with a circle, what are we dealing with? Think circle, think pi. Okay? To do any calculations with a circle, you need to be thinking about pi. So anybody know how to work out the area of a circle? Good. So you need to learn this one off pat.
Wowie.
And sometimes it's welded into your brains. Okay? The area of a circle is pi times, what's our?
Radius.
The radius squared. Okay? It's that thing that goes from the centre to the outside. So remember early on I said you've got to know the difference between a radius and a diameter and a radius because they're going to swap them around. we're going to do a question that will give you some practice on that. So let's just do one together that's really basic. So the area of a circle is pi r squared. I've got a circle with a radius of 10 centimetres. What's its area?
3.14.
So I know that pi is 3.14. And it
10
times
centimetres.
yeah,
Times 10 centimetres.
squared. Okay? What rule tells us what to do in what order when we have something like that?
Is it the radius squared first?
Yeah, so BIDMAS tells us the I in BIDMAS is indices, so you do the 10 squared first and then you multiply it by 3.14. So it becomes 3.14 times 100, which we can now do off the top of our heads because we can multiply and divide things by 10 and 100 really quickly. 314. And don't forget the units, which are,
7.
and what else? Because it's area squared. And we'll come on to that in a couple of weeks. Okay? So here's 2 questions for you. Last questions of the day, just about. Okay? Find the circumference and area of that circle. And then the second question is a bit harder. I want you to find out the diameter if I give you a circumference. So there's a bit of algebra involved.
This on the
Let's talk about it. So how do I work out the circumference of this circle, first of all? What do I need to know? What's the formula that kickstarts it all?
Pi times diameter.
So the circumference of the circle is pi times diameter. You might not get given this in the exam. They will expect you to know that off the top of your head. So you need to get that into your heads, okay? That the circumference of a circle is pi times the diameter. Okay, so what do we know that we can fill in on this formula? I know pi is 3.14 and my diameter is 12. So the circumference of this particular circle is 37.7. Everyone get that to one decimal place. And that is centimetres, don't forget the units. So let's look at the area then. How do we calculate the area of a circle? Pi times the radius squared. Everyone happy with remembering that? They ain't going to give it to you. Okay? What do we know? Pi is, and the radius is
6.
Ah. So it's 6 squared. That gives me 113.0 something like that. So to one decimal place, it's 113. Happy with that? Perfect. Let's look at the last one. It's a trickier one, bit of an extension task for you, okay? Anybody have a crack at that one? Where do we start?
I don't know if I got it right.
Well, let's talk through it then. Where do we start? What do we know?
I wrote out the circumference formula.
Yeah, so circumference is equal to
Pi times diameter.
pi times the diameter. Good.
And then I did
Put in what you know.
3.1.
So you know that pi is 3.14. I'm happy with that. But what are they giving you this time?
Circumference
Which is
22.3.
22. Can't write it over here. 22.3. And then what's the thing that we don't know? So 3.14 is doing what to that? It's multiplying the diameter. Can you see that? So all we've done is a bit of algebra. We've put in the numbers that we do know. We know the circumference is 22.3, which is on the left-hand side of our equal sign. And we know that pi is 3.14. And the thing that we're looking for is the diameter. So we need to get the diameter on its own. So using our algebra skills now, how do I get d on its own?
Do you divide the circumference by the pi? Or
Brilliant.
by the
So to get d on its own, I have to divide this by 3.14 because they cancel each other out and leave d on its own. I'm doing the opposite, multiply, divide. But if I divide that side, I have to divide that side. So I've now got d on its own on that side, and this side has 22.3 divided by 3.14, and that gives me 7.1. Yeah. Everyone happy with that?
No, I rewrote the formula before putting the numbers in.
Brilliant. Absolutely nothing wrong with that at all. Yeah? You can rewrite the formula before you put the numbers in if you want to, or substitute what you know and then move the numbers around. It's perfect, whichever way you've done it. Everyone happy with it? And they're the sort of the extension questions they can ask you. Excellent. Excellent. Right, we've completed the 3 objectives for today. Pretty full lesson. The time is now 12:10.
You just 2 hours and 10 minutes, don't you? 2 hours.
Well, we've still got the 20 minutes. It still goes to 12:30. Still got the 20-minute homework club if you want it. Okay. Objective 1, recall the properties. Basically, objective 1 was about the shapes, 2D and 3D shapes. We've now covered. We've got the names. We've learned some angles. Second objective was all about labelling a circle, talking the language of a circle. And as Sam said, it comes up really frequently. And 3, doing areas and circumference of a circle using this magic thing called pi, which isn't so magic anymore. We know what it is and where it comes from. Think string. Anyone got any questions on what we've covered today?